All right, in this presentation on glaciers, we'll go over some of the features of glaciers, the characteristics of glaciers, factors that influence whether they are advancing or retreating. Just a reminder that uh, glaciers are a large store of fresh water, so of the 3% of fresh water on the planet, the majority of that water is stored as ice caps in glaciers. And so we would like to keep it that way, but our few graphic images that show the change in areas over time. Here we have the same area in 1941 and again in 2004. You can see that there's dramatically less ice in that location. Another similar picture, larger time gap between the two. So sure, these glaciers have advanced and retreated over time. The concern here is that humans are largely responsible for the recent decline in the amount of ice. All right, so it's important to note that glacial ice is different than snow that falls. So snow goes through a few stages before it finally becomes firn, which can survive into the next winter and eventually be locked up as glacial ice. So it's that glacial ice that we're talking about in glaciers. All right, so there's two types of glaciers. Those that are found at high altitudes, up at the tops of mountains. And then the second category are at high latitudes, those that we find towards the poles. So first, alpine glaciers. These are on all the continents, and it doesn't matter what the latitude is because these are high elevation areas. So usually colder and wetter and constrained to valley channels. And so most of our talk will be about alpine glaciers. The second category is the continental glacier, or called an ice sheet. So these are large in area. They're unbounded, and that they can flow in all directions. So we've talked about that a little bit in the past as evidence for Pangea. Note in the picture below we have a topographic map with a cross-section from A to A prime and B to B prime that shows us the glacial ice, but also the land underneath. Presently, we only have two locations that have these at high latitudes, Greenland and Antarctica. All right, so we'll see this picture again. It shows some of the features and the different zones of accumulation and ablation. So we'll return back to this, but we see a lot of the characteristics of a glacial area. Even if the glacier is removed, those characteristics remain behind. And so there's a difference between an area that was glaciated and an area that was formed more from rivers. All right, so we've talked about how water moves, and we'll do the same thing with glaciers. So glaciers can move by two processes, flow and slip, that are described on the next slide. Just like with groundwater, the ice flow rate varies from place to place. In the simulation, the FET simulation, we can manipulate some variables to change the flow of ice. We can manipulate the amount of snow, the temperature, things of that nature. All right, so there's two types of movement that we talked about on the previous slide, plastic flow and basal slip. So I think the term basal slip here, when you think of base, is easy to remember what's going on there. This is the sliding of the glaciers along the boundary of the ice and the ground, the base, the ground. Whereas plastic flow is the slippage between individual ice crystals. And so we'll see this in a picture on the next few slides. But just like with water, the center flows faster than the sides. And so both of these are taking place, but the ratio depends on the steepness and the thickness of ice. Note that the last bullet says continental glaciers move mostly by basal flow, whereas valley glaciers move mostly by plastic flow. All right, so here we have a glacier. We have some rocks that are embedded in it, and note that the ice is frozen to the ground. But there's also friction there, so the top is going to move a little bit faster than the bottom. So this you can see in the simulation. You can drill into the ice and see this with the drill holes. As the drill holes move, it kind of, if you connected the end of these arrows, that's kind of what the motion would look like of the drill hole. It was straight up and down, but as the top moves faster than the bottom, it gets bent a little bit at the bottom. And so you can see that in the simulation. But you can't see the cross-section in the simulations. It's a side-on view. As we move away from the side of the channel where there's friction and again some freezing, it moves faster towards the center. So here that's shown with a series of stakes that have been pushed into the ice. Okay, and then I think these two terms, at least the first one, makes sense, the zone of accumulation. So this is the area where it's the upper end of the glacier where it's covered by year-round snow. Ablation is the melting area, so lower and melting in the summer, hopefully just the summer. And then there's the line that separates those two areas, the zone of accumulation from the zone of ablation. That's the snow line. Now again, these are on the simulation, and I think it's a red dashed line, if I recall, that is the snow line. It separates the two. So that's essentially where we have a zero factor. So in the zone of accumulation, you're accumulating, so there's more and more snow, so it's growing. The zone of ablation is shrinking, and at the snow line, it's a net effect of zero. It's neither growing nor shrinking. All right, so this should be, knowing those kind of definitions, this should all make sense. If ablation, if melting exceeds accumulation, the glacier is then retreating, right? If accumulation exceeds ablation, then the glacier is advancing, it's growing, and moving down the mountain thicker. All right, so that's shown here. So here we have this dashed line, or snow line. We have the accumulation part above that. We have ablation, and we'll talk about a few ways that ablation can happen. So here you see some of those. Sublimation, so the ice going directly to a gaseous state before it melts. We do have melting, and then we have this calving that can happen where the ice breaks off into the water. So all of that leads to ablation. All right, and then what we just said in words earlier, if accumulation equals ablation, then this dashed line kind of stays where it is. If accumulation is greater than ablation, then this dashed line moves downhill. And if accumulation is less than ablation, then this retreats and this snow line moves up the hill. All right, so I'll play this video here, although you can watch it at home. Hopefully it will link here. I'll have to drag this over. All right, so here we have calving. I'll fast forward a little bit because there's some more dramatic. All right, so obviously those folks were, I think, happy to be in the location to be able to see that, but that's not a great thing to see because we are watching the ablation take effect. In other words, we're watching the shrinking of the glacier there, which is something that we're trying to prevent from happening. So, so calving, that's one of the ways that a glacier can shrink, and what you'll see left in the water was the icebergs. There was a moment there where they panned down, kind of smaller icebergs, but icebergs nonetheless. Sublimation I mentioned on the previous slides, ice going directly to a gas state passing the water state, so that would just be melting. And then wind erosion as well. All right, so that brings us to the characteristics. Unfortunately, there's just a lot of terms here. Some of them are similar, and so we want to point those out. All right, so first, during glaciation, the characteristic of a glacier compared to a channel that's been formed via a river is the U-shaped valley that you see here. That U-shaped valley is characteristic of the glaciation as opposed to a V-shaped channel, which you see with a river. All right, so here's our U-shaped valley. We have this hanging wall, so it's not uncommon to see these beautiful waterfalls coming out. And then we have just a series of terms here that you'll interact with a little bit on the FET. All right, so here we have this nice bowl or cirque that is the head of the glacial valley. These very jagged crests called arêtes. There's our U-shaped valley with its hanging wall with a beautiful waterfall. Right. Here we have the glacial till that's left behind as a esker. We have talked a little bit about this before when we looked at evidence for Pangaea's existence, that as the glaciers move, they have huge amounts of sediment that can scrape into the surrounding bedrock and leave grooves, and these show the direction of glacial movement. And so here we have a picture of these glacial striations with the till or the material that was locked in the glacier as it was moving. And here we have stones that were carried by the glacier, that when the glacier melts, it deposits these large glacial drop stones. It's these large drop stones, again, that can scour the earth and leave these striation marks. All right, so any material that is found in the glacier, and in the simulation, you'll see the till is the black dots that are mixed in the ice. And this is just a mixture of things like rocks, sand, clay, any kind of debris. So then we have these accumulations that form when the glacier kind of stays static. So you'll see that in the simulation, when you keep ablation equal to accumulation, it's neither advancing nor retreating, and so we get a moraine that's formed. Okay. You'll see it better than if you do that, and then you cause ablation to exceed accumulation, and the snow line moves up the mountain. Then you'll see left behind that till. Okay, so that leaves a series of moraines, and you can see that there's some here and on the next slide. So the end moraine is what it sounds like. It's the what I just mentioned in the simulation. It's the end point of that glacier if it stays in the same place for a while and drops a bunch of till. All right, that is similar to the terminal moraine. So the terminal moraine is a sort of end moraine, but it's the lowest down the valley that you would find this till. It's the terminal end. Okay. And then a recessional moraine, again, just and you can make this happen in the simulation as the glacier moves up and retreats, different points where that till kind of drops out. And then lateral and medial are kind of what they sound like, medial middle. These are where two glaciers come together and meet. We have a picture of that on a slide coming up. And lateral is along the edges. So again, better shown with a picture here. All right, so here's the picture that we looked at before. We have lateral along the side, moraine, We have medial, where these two glaciers coming down from these two different valleys come together, and that glacial debris is now